All right, so now that we have covered the mean value theorem, we're going to look at some examples involving that theorem, applications of it, I guess you could say. So to start with, we're going to just look at a function that will satisfy the hypotheses of the mean value theorem and then try to find the value c that's guaranteed by that theorem. So this one's not so much an application as it is kind of just getting used to the theorem itself. So the function is f of x equals x cubed minus 3x plus 2. And remember, the mean value theorem, or the MVT, only has two hypotheses that we need to satisfy, as opposed to the 3 hypotheses in Rolle's theorem. Here's the closed interval that we're looking at. There's always going to be a closed interval involved somehow, because that's in the statement of the theorem. So to show that it satisfies the hypotheses, notice that the function is a polynomial. F of x is a polynomial, and is thus continuous and differentiable everywhere. So it must be continuous and differentiable on the closed interval -2, 2. If it's differentiable and continuous everywhere, then clearly that's the case here. And it only needs to be differentiable on the open interval -2, 2, but if it's differentiable on the closed interval, the open interval is a subset of this, so it's obviously going to be differentiable on the open interval -2, 2 as well. So that means it satisfies the hypotheses of the mean value theorem. Okay, now in order to find the value of c that we're guaranteed by the mean value theorem, let's come back. Actually, right here is a statement of it. We need the slope of the tangent line at whatever that value happens to be equal to the slope of the secant line passing through the points that correspond to the endpoints of this interval. So we can find this side with what we're given, and we can then use that to find this side. A, in this case, is -2, and B is 2. So I want to start by finding f of 2 minus f of -2 over 2 minus -2. Okay? Now this is not hard to plug these values in to this. It's just a polynomial. You can do this mentally or in a calculator or whatever you want to do. But f of 2, when plugged in, works out to 4. F of -2 works out to 0. And this down here, 2 minus -2, is 4. This comes out to 1. So what that means is that the secant line passing through the 2 points on this curve given by the endpoints of this interval has a slope of 1. So what I need to do is find a value c in between -2 and 2 such that the tangent line at that point has a slope of 1 as well, a slope equal to this. So in order to do that, I first need to find f prime of x to then find that slope. So what I'm going to do is say f prime of x is equal to what? Well, I'm going to differentiate this directly. 3x squared minus 3. And I want to set that equal to 1. Okay? So and I'm going to plug in a c to do that. So this derivative, when I plug a c into it, with the c that we're looking for, 3c squared minus 3, should come out equal to 1. Okay? I want to solve this for c. So I'm going to get c squared equals, if I add 3 over, that's going to be 4. Divide by 3, I'm going to get 4/3. So 4/3. Taking a square root of both sides, c is equal to plus or minus, the square root of 4 is 2 over root 3. All right. Now, 2 over root 3 and -2 over root 3 are both contained in this interval. So in this case, I've actually found 2 values of c that will work. I can call the 2 of those together my answer. Okay? So that's our first example. Let's take a look at another example. And this is kind of a bizarre one just when you first read it. But then if you look at how the mean value theorem applies to it, it's not too difficult to see what we have to do. It's a little bit different than any kind of problem we've done so far. I'll say that much. Let's suppose that we have some function, f of x, and we don't know anything about it other than what we're told here. So I don't have an algebraic representation of that function to look at. I don't have a graph to look at. I'm just working with the information that I'm given. We're going to suppose that f prime of x is less than or equal to 3, greater than or equal to 3, and less than or equal to 5. So between 3 and 5 inclusive for all values of x. Okay, what this is doing is it's putting a lower and an upper bound on the slope of any tangent line to this curve anywhere in its domain. Okay, and it says all values of x, where that would imply that it's defined everywhere. We want to show that f of 8 minus f of 2 is bounded by 18 and 30. It's between 18 and 30 inclusive. So the way I'm going to do that is I'm actually going to start by looking at this. F of 8 minus f of 2 looks kind of like f of b minus f of a in the statement of the mean value theorem. So that kind of gives me an indication as to what closed interval I should be concerned with. The closed interval 2, 8, because that would be a and b. So now, not only that, it says that f prime of x is bounded by these two values for all values of x. That actually implies that f prime of x exists everywhere, which means that f is differentiable everywhere. So f is differentiable everywhere, implying it is also continuous everywhere. Because we had a theorem way back when that says that if a function is continuous on some set of numbers, then that, if it's differentiable, then it's automatically continuous there as well. So if this is true, and again, this is all implied by the fact that we have this statement that says f prime of x is between 3 and 5 for all values of x, which implies that it exists in the first place. We can say this, so it is continuous and differentiable on the closed interval 2, 8. Remember, these values here were the clues that we should be looking at the closed interval 2, 8. So this confirms that the hypotheses of the MVT are met, which means we can apply it. So by the mean value theorem, the MVT, there exists a number C in the open interval from 2 to 8 such that f prime of C is equal to f of 8 minus f of 2 over 8 minus 2. That's the slope of the secant line that we've been referring to. This is the same as f of 8 minus f of 2 over 6. Okay, now looking up here, I have f of 8 minus f of 2 appearing in some of my given information. So I'm going to take this and multiply both sides by 6 so that one of my two sides looks like f of 8 minus f of 2, allowing me to sort of access this information. So f of 8 minus f of 2 is equal to, multiply by 6 times f prime of c. All right, now according to what we're told here, f prime of x is between 3 and 5 for all values of x, which would include c as well. We know that this is true. F prime of c has to be between 3 and 5 inclusive. So I know something about 6 times f prime of c here. I'm going to multiply everything by 6 and see what that gives me. Multiplying by 6 gives me 18, less than or equal to 6 prime f of c, less than or equal to 30. Notice now I have those numbers that were appearing up here. The fact that 6 prime of, I don't know why I wrote 6 prime, 6 times f prime of c, which we have here, is exactly equal to f of 8 minus f of 2, means I could substitute this for this. Therefore, this must be true. Okay, which is what we were trying to show in the first place. is an odd problem. It's an unusual problem, but we can see where the mean value theorem came into play in proving that this must be the case. Okay? One last example, then we have a couple of theorems to talk about, and we'll be all done. So this example kind of illustrates a really practical application of the mean value theorem. It says that a driver is traveling on a highway with a speed limit of 60 miles per hour. 1 minute later, he passes another police officer 2 miles down the highway from the first officer who clocks his speed at 55 miles per hour. Should this driver be issued a speeding ticket? Well, when he passes each officer, he's going at or just below the speed limit. So based on that, if that was all the information that we had, the answer would be no. It doesn't appear that he's speeding. But we're given more information than that. It says 1 minute later, he passes another police officer 2 miles down the highway. So it took him 1 minute to travel 2 miles. Okay? Let's think about that for a moment. I'm going to define the position function. S of t is the distance between the driver and the first officer. T hours after passing the officer. Okay? So based on that information, S of 0 would equal 0. Because at time equals 0, that's exactly when he's passing that first officer. So his distance from that officer is 0 miles. I should say distance in miles. Okay? The next officer, he reaches after 1 minute. So after 1 minute, because time is measured in hours, I would think of that as 1/60th of an hour. And at that point, he's traveled 2 miles down the road. He's now 2 miles away from the first officer. So that would equal 2. Okay? So what is the average speed that this guy was traveling? Well, average speed would correspond to the slope of the secant line on this interval from 0 to 1/60th. That would equal S of 1/60th minus S of 0 over 1/60th minus 0, or 2 minus 0 over 1/60th, which is equal to 120 miles per hour. That's his average speed. Even though neither officer clocked him going that fast, that is his average speed. However, in order for him to get a speeding ticket, we have to know that he was actually traveling at least that speed at some point between those two officers. So in order to show that, this is where we apply the mean value theorem. S of t is continuous and differentiable on the interval from 0 to 1/60th. The reason why that's the case is because we've talked about this before. Most functions that kind of model something natural, like speed and distance and things like that, are continuous and differentiable by default. Because in order for them not to be continuous, say if it were to have a jump discontinuity or something like that, that would be like teleporting from one place to another in an instant. That doesn't happen, right? So it's okay to assume that S of t is both continuous and differentiable on this interval. That means that we can apply the MVT. So by the mean value theorem, there exists a number C in the interval from 0 to 1/60th such that f of c, or f prime of c rather, is equal, we're calling our function s. S prime of c is equal to s of 1/60th minus s of 0 over 1/60th minus 0, which we just showed was 120, right? But remember, s prime, if this is a position function, the derivative of a position function is a velocity function. So what that means is, according to the mean value theorem, there actually was some instant between when he passed the first officer and the second officer at which time he was going exactly 120 miles per hour. So it's no longer just an average speed, it's his exact instantaneous velocity. So yes, he should get a speeding ticket. That's absurdly fast, right? Okay. We just have a couple more things to talk about, and then we're done with section 4.2. These two theorems are extremely important, particularly this second one, when it comes to antiderivatives and integrals, which we talk about at the very end of chapter 4 and then all throughout chapter 5. And then calculus 2 is very much concerned with integrals. But we're not going to make that connection yet. We're just going to lay the groundwork here. So this first theorem says that if f prime of x is equal to 0 for all x in an interval ab, then f is constant on that interval ab. Now that seems intuitive, because if f prime of x is equal to 0, that implies that we have a horizontal tangent at that point, a horizontal tangent line. And this is saying that if all of the tangent lines at all of the values between a and b are horizontal, then we must be looking at a horizontal line, which is the graph of a constant function. That seems intuitive, but that's not really a proof. That's just what our mind tells us should be the case. So the proof looks like this. We're going to assume that this is true, that f prime of x is equal to 0 for all x in this open interval. And we're going to let x1 and x2 be any two numbers in this interval where we assume that x1 is less than x2. Okay? Now, because f prime of x is equal to 0 for all x in this interval, that implies that f prime of x exists, which means f is differentiable on that interval. And so it must be differentiable on this open interval as well, x1 to x2, because those two values are contained in AB. So this entire interval is also contained in there. Not only that, the closed interval x1, x2 is also contained inside that interval. And because we know that f is differentiable everywhere in that interval, it must be continuous everywhere in that interval as well, which would include the closed interval x1, x2. The point of stating this is because this is showing that the two hypotheses of the mean value theorem are satisfied, which means we can now apply the mean value theorem to our function f on this interval, x1, x2. According to the mean value theorem, we must have a number c between x1 and x2 such that this is true. Now remember, when we stated the mean value theorem, which back to where I stated that, this was the alternative form that we gave to the one we've been using, just by multiplying both sides by b minus a. So that's totally valid to say, according to the MVT. Now, because f prime of x is equal to 0 for all values of x, c is a number, so f prime of c must also equal 0, implying that this entire right-hand side is equal to 0. Leaving me with this, f of x2 minus f of x1 is equal to 0, or equivalently, f of x2 equals f of x1. Now think about what that means. We selected x1 and x2 completely arbitrarily. We only assumed that they were not equal to each other, that's what this inequality would imply, and that they were between a and b. So what this is saying is that for any two numbers that we select in this interval ab, f of each of those numbers is always equal to the same thing. But that is actually the very definition of a constant function. F of any number in that interval always gives me the same number, the same constant. Now that alone is important, but kind of intuitive. It's not a huge surprise that that's true. What's more important is this corollary, the thing that it implies. A corollary is a theorem that is a direct consequence of some other theorem. So that's why this is saying corollary here. This corollary says that if f prime of x is equal to g prime of x for all x in an interval ab, then f minus g is a constant on ab. Or in other words, if f of x minus g of x is equal to some constant c, I could alternatively write f of x equals g of x plus c by adding the g to both sides, where c is a constant. The way we show that is we define f of x to equal, big capital F of x, to equal little f minus little g. Then differentiating both sides of this gives me f prime of x equals, big F prime of x equals little f prime of x minus g prime of x. And that would equal 0 because we have assumed that f prime of x is equal to g prime of x right here. So their difference must equal 0. But according to that previous theorem, this function would have to be a constant if this is true for all x in that interval. So because we define big F to be little f minus g, f of x minus g of x must be constant. Now the reason that's important is because at the end of this chapter we're going to talk about antiderivatives, which is if I give you a function, say 3x squared, the question is, can you find a function that has this as a derivative? So I'm not taking the derivative of this. Instead, I'm looking for some other function for which this is a derivative. Well, one such function is x cubed, right? I know that if I differentiate x cubed, I get 3x squared. But the question is, are there other functions such that this is true? And the answer is yes, but this corollary says that any other function that has a derivative equal to 3x squared must look like x cubed plus a constant. So for example, d dx of x cubed plus any constant would also equal 3x squared. But no other functions can have 3x squared as a derivative. Okay? You need to remember this theorem for the end of chapter 4 because that's when we're going to use it. But that's going to wrap up 4.2 for us.